We're going to address the topic of addition and subtraction of radical expressions and a little bit more with multiplication. When you add and subtract radical expressions, it's just like adding and subtracting like terms algebraically. For example, 2x plus 5x equals 7x because those are like terms. They have the same variable, the variable's raised to the same power, and so you add their coefficients. Radical expressions can only be added and subtracted if the number under the radical is the same, or the expression under the radical is the same, and you're taking the same root. For example, you're working with both square roots, or so. At first glance, this problem looks like that the terms could not be added because the number underneath the radicals are not the same. And if I could not simplify this problem could not be simple. If I could not simplify each term, the problem could not be simplified. But I can. I can take the square root of 12, and I can think of that as the square root of 4 times the square root of 3. And I'll bring this 9 out in front. And let's go ahead with the 27. I'm going to think of the square root of 27 as the square root of 9 times the square root of 3. And now I'm going to simplify those which are perfect squares. In this case, the square root of 4 is equal to a 2. So I have a 9 times 2, or an 18, out in front of this square root of 3. I'm going to go ahead and finish that. And then over here, the square root of 9 is equal to 3. And I've got essentially then 16 times 3 in front of the radical, the square root of 3. This product right here is 48. And now I'm able to add because I have like terms now. I have the square root of 3 as my radical expression for each of these. And now I can combine the 18 and the 48. I'm going to write that down just to make mention that that's what we're doing. We're collecting the coefficient times the square root of 3. And it looks like that's going to equal 66 times the square root of 3, and we've successfully added those two terms. Again, we're just adding and subtracting radical expressions, so I've got to simplify these first before I can combine these in hopes that there are like terms. I've got to think of two numbers that multiply together to be 50. While 5 times 10 is a possibility, neither 5 or 10 are perfect squares. So I have to keep thinking. I have to remember that list of perfect squares. And I recall that 25 is in the list of perfect squares, and 25 goes into 50 2 times. So I will write the square root of 50 as the square root of 25 times the square root of 2. And I'm going to go ahead and simplify this statement. Since this is equal to 5, I have 5 times 5 out in front, or 25 times the square root of 2. I've successfully simplified the first term. The next term, the 18, I'm going to write that as the product of two radicals, being 9 and 2 because their product is 18, and the square root of 9 is a perfect square. It's equal to 3, and I have to multiply that by the 2 that's in front of it, which gives me 6 times the square root of 2, and it looks like I'm going to be able to collect some like terms. And finally, the 32 needs to be broken into the product of two numbers, and it's not enough to use 4 and 8. While 4 is a perfect square, it's enough if you go as high as using the 16 times 2. This is the largest perfect square that divides into 32 evenly. You've got to get that. and then this number is equal to 4. I need to multiply that by the 9, and 9 times 4 is 36 times the square root of 2. And it looks like now I can collect these because these are like terms. They all have the square root of 2 in them, and I'm going to combine their coefficients. I'm going to go ahead and do them one at a time, working from left to right. So 25 minus 6 is 19 times the square root of 2. And now I want to add the 36 times the square root of 2 to that. And it looks like I'll get 55 times the square root of 2. In this problem, we're going to do a subtraction problem, but please notice that the indices are different. We're looking at cubed roots here. So what I have to be comfortable with or careful is to recognize perfect cubes. And I've listed here some of those, starting with 1. And the next perfect cube is 8. It results by taking 2 to the third power. The next perfect cube is 27. And then 64. These are all numbers that I can take the cube root of and get a whole number, or a natural number for that matter, as a solution. So when I break this 54 up into the product of two terms, I'm going to use 27 times 2 because that product is 54, and that's the largest number in this list that will divide into 54 evenly. I got to remember to keep this x in here. I'm going to put these under their own radical because they are not perfect cubes. There's nothing I can do with this. The cubed root of 27, however, is equal to 3 because 3 times itself 3 times gives you 27. There's the first expression, or first term simplified. The next term, I'm going to write underneath one radical, and I want to remind you that I'll take this variable x to the fourth and write it as the product of two factors, x to the third times x to the first. Those exponents add to be 4. And I purposely made this a 3 because if it is divisible by the indice, then it's a perfect cube. The cube root of x to the third power, remember, is just x. It's this 3 divided by 3 is 1 as an exponent. And I'll have now x times the cubed root of 2x. The good news here now is that these two terms are like terms, and I can collect those like terms. The bad news is that the coefficient in front of each of these terms are not like. It's not like I have a 3 here and a 5 here and I can subtract, take 3 minus 5. So what I have to do, since they're not like terms, is I just have to state those in parentheses, 3 minus x times the common factor here, the cubed root of 2x. If I didn't put parentheses here, this would be incorrect because you would be stating for me that I have a minus x times the cubed root of 2x. It is not just a minus x. It is 3 minus x times the cubed root of x, and this is the way I have to state this. Here's an unusual problem. I want to add these two radical expressions. And I've got terms now underneath the radicals. So far I've had factors underneath the radicals. But what I can do is I notice that I have a greatest common factor in these two terms right here of 9. So I'm going to factor that out. And I'll have 9 times y plus 3. I'm going to break this down while I don't know that it's necessary for you to see this. That's essentially what I have. This square root of 9 as its own factor. The square root of y plus 3 is its own factor. And now I can take this perfect square here, the square root of 9, and write it out in front as 3 times the square root of y plus 3. I'm going to bring down the second term. It is the same. The value under the radical, or the radicand, is the same. So these are terms that can be collected now. What you just have to remember is that there's an understood 1 in front of that radical, because I have to combine their coefficients. So I have to take this 3 and this 1 and add them together to get 4 times the square root of y plus 3. And now I've successfully added these two radical expressions. We're on to the second objective for this section, and that's the more multiplication part. We've kind of finished with a few problems of addition and subtraction. So this is a multiplication problem that we're going to take a look at. And it's very, very much like the distributive property with a typical monomial times a binomial. And so there's a couple things I want to do comparatively before we do this problem. First of all, this problem behaves just like this problem, and that I would take 6 times 2x and get 12x, and 6 times 3 and get 18. So I'm just going to distribute, number one. second thought to be reminded of. If I take the square root of a number times the square root of the very same number, I'm going to go ahead and do this a long route, if you will, just to prove something. The square root of 2 times the square root of 2 is the square root of 4. And I know that the square root of 4 is equal to 2. So what I need you to remember from here on out is that whenever you have the square root of, I don't care what the number is, times the square root of the very same thing, you always get that number as a result. Again, the square root of 2 times the square root of 2 is 2. The square root of 3 times the square root of 3 is 3. The square root of 100 times the square root of 100 is 100. And so over here, when I get ready to distribute this, let's go ahead and look at the first term. I have the square root of 6 times 2. I'm going to write the 2 in front. It's just a practice, it's a habit, it's a policy in math that we will put the coefficient in front of the radical. So not vice versa. We won't write the square root of 6 times 2. We'll write 2 times the square root of 6. And then you need to remember that the square root of 6 times the square root of 6 is just 6, as we showed over here. And we're done. We've multiplied. When we do some of the multiplications that problems that follow, what I want you to remember is that multiplication is a commutative process. 2 times 3, 3 times 2. It doesn't matter. You get 6. So I'm going to be writing some of these factors in different orders so that it will make the process of multiplication simpler for me. So when I take the square root of 2 times 3 times the square root of 10, I'm going to purposefully put the 3 in front, and I'm going to be thinking the square root of 2 times the square root of 10. That's the order I want to think of it, and it's because these two can be multiplied together, and I can get the square root of 20. So ultimately, this will be 3 times the square root of 20 when I multiply these two together. Likewise, right here, when I take the square root of 2 times this 2 times the square root of 2, I'm going to put the 2, this coefficient, out in front, and I'm going to think square root of 2 times the square root of 2. I'm going to write that down for right now and not take that jump to the correct solution for that right away. I just want you to see all the factors together. And now we might take an intermediary step here. We've said the square root of 2 times the square root of 2 is 2, and I have to multiply it times that 2 out in front. So what I have here as a second term is a 4. Finally, I shouldn't stop there. I know that the square root of 20 can be simplified because I know that can be written as the product of two numbers, 4 and 5, where one of them is a perfect square. Don't lose this 3. Don't lose your 4 here as your last term. And then remember that the square root of 4 is equal to 2, and you've got to multiply it by the 3 out in front. That right there is 6 times that square root of 5 minus 4, and I've completed that multiplication process. No more simplifying can be done. These aren't like terms. I have to leave that alone. This problem is called the sum and difference of like terms. Just like algebraically, when we've had two binomials that we multiply together, where the first terms are alike, the last terms are alike, but there's a plus sign in one and a minus sign in the other, and we FOIL it. Before I even do this problem, I just want to remind you of a similar circumstance algebraically. Let's take 5x plus 6 times 5x minus 6. When I FOIL this right here, I'll have a 25x squared as my first term. And remember that these outer here, which is a minus 30x, and the inner products here, which is a positive 30x, those always add to be nothing when I multiply these kinds of binomials together. And this 6 times a minus 6 is a minus 36. So what I end up with is 25x squared minus this 36, and I lose the middle terms. Similar circumstances are going to occur here, and I'm not even going to bother to write those middle terms down from here on out. Let's get rid of this. So when I distribute or FOIL this, the square root of 5 times the square root of 5 is just 5. And then right here I have a minus the square root of 30, and here I have a plus the square root of 30. Those add to be nothing. And then this plus times this minus is a minus. Square root of 6 times the square root of 6 is 6. This problem boils down to a -1. Here's another problem where we're going to FOIL. I've got two binomials, not quite like the last ones where they're the sum and difference of like terms, but similarly I'm going to multiply the first terms right here together. So I have 4 times the square root of 3 times the square root of 3. I need to skip a step now. I need to save some space, some time, save you some time. The square root of 3 times the square root of 3 is 3. So what you have there is 4 times 3 is your first term. The outer terms multiply to be, I'm taking this 4 times the square root of 3 times a minus 2. So first of all, a minus sign. This 2 times this 4 can be multiplied to be 8 times the square root of 3. Right here, I have a 5 times the square root of 3, and it's positive. I'm going to put it underneath this other term because they're like terms, and I'm going to collect them like I did algebraically when I multiplied two binomials together. And 5 times a minus 2 is a minus 10. And so finally here I'll have a 12 in front. This minus 8 and this positive 5 collects to be a minus 3 times the square root of 3. And I'll bring down this minus 10. And unlike algebraically, when I'm multiplying two binomials where there's variables involved, I have some like terms to combine still. 12 minus 10 is 2. And then I'll bring down my minus 3 times the square root of 3. And I have now successfully multiplied these two binomials. Again, I just want to FOIL these two binomials. So let's go ahead and take the first terms. 2 times 1 is 2. 2 times a minus square root of x is a minus 2 square root of x. And a minus square root of x times 1 is just a minus square root of x. If you'd like, put a 1 here because its coefficient is truly that 1. A minus times a minus here is a positive, and the square root of x times the square root of x, remember, lose that radical, is just equal to x. So I'm going to collect my like terms right here. Because the radicand is the same underneath that radical, I can add the coefficients. So a minus 2 and a minus 1 is a minus 3 times the square root of x plus this x, and I'm done. I pose this problem, a binomial squared, because I've been experiencing some of my online students when taking a binomial and squaring it, forgetting to write the binomial out 2 times. And what they do is they think that all I want you to do is to take the square root of 5 squared, which is 5, and 1 squared, which is 1, and add them together. But that's not it. What I'm looking for here is for you to take the square root of 5 plus 1 times the square root of 5 plus 1. If you've any trouble in the polynomial section, which would have been, I believe, chapter 4, in failing to take a binomial that is squared and writing it out 2 times, that's the reason. And now you truly just FOIL this. The square root of 5 times the square root of 5 is 5. And here I have 1 times the square root of 5. I'm going to go ahead and put the coefficient there so you can recognize it or see it. And this 1 times the square root of 5 will be collected in a minute here. And then finally 1 times 1 is 1. And so I'll have this 5. And here I collect their coefficients. 2 times the square root of 5 plus that 1. And the 1 here and the 5 here have to add to be 6 plus 2 times the square root of 5, and I have squared this binomial. Similar to the last problem, I want to take a binomial and square it, but the radicals involved here have indices of 3, or I'm taking cube roots. So the first thing I might consider doing in this problem, since I have the cubed root of 8, x as well, but the cubed root of 8 is just equal to 2. I'm going to factor that out first in front before I go ahead and multiply. So again, I'm taking this piece out, and that is equal to 2 times then the cubed root of x. So there's my first term in this binomial, and then I have the cubed root of 5y. Well, I want to square this, so I'm going to write this out a second time. So I have 2 times the cubed root of x minus the cubed root of 5y. And again, I'm going to FOIL it now. So what I have here, be real careful with this, I have 2 times 2, which is 4, and the cubed root of x times the cubed root of x, be awfully careful, is not just x, it's the cubed root of x squared. This would only be x if it was the square root of x times the square root of x, would give me x. But this x times this x is x to the second power, that cannot be reduced. Then right here what I have is a minus 2, I'm going to put that in front, times the cubed root of x 5y, or I'm going to put 5xy. And then here I have another minus 2 times the cubed root of 5xy. So it happens that those are going to be like terms. And finally, I have these last terms to multiply together. A minus times a minus is a positive. The cubed root of 5y times the cubed root of 5y is the cubed root of 25y squared. I multiply what's underneath the radicals, and it's not something that's a perfect cube. I cannot simplify this. So finally, what I'm left with is 4 times the cubed root of x squared. I'll combine these coefficients because these are like terms, so I have a minus 4 times the cubed root of 5xy, plus finally the last term, the cubed root of 25y squared. This is the end of our multiplication section. We're going to go on next to section 5.